Okay, very good. So once everyone is settled down, we'll get going with the final couple of talks of today and of the conference. So it's a great pleasure to introduce Jules, who's going to tell us about the Heisenberg spin chain and its long-range friends with no strings attached. Please.
So thank you very much. So I would like to thank the organizers for giving me the possibility of presenting some of my work of the past years in this community. So as some of you know or may vaguely have realized, I originally scientifically come from this community, although I never really worked in it. But I attended some IGSTs at the start of my PhD, and so it is actually very nice to be back in this community, see some people again, some familiar faces as well as new people in the field, and hear about the progress. So that's been really interesting. For me, I hope to tell you something about something which I think could be interesting for you guys. So it's indeed about a long-range perspective on the Heisenberg spin chain and some related spin chains. So I will really only be talking about quantum-integrable models, only at finite length. So those are some disclaimers, no strings attached. So just either mathematical physics or condensed matter if you wish. And this is joint work with Rob Klabbers, with Vincent Pasquier and Didina Serban, who are also in the IPhT in Paris. And it's also ongoing work with Rob, Didina, and our master student, Ayman Toufik. My goal is to show some of the models that I've been thinking about, to show you what kind of structures you can have for long-range Hamiltonians. And they look a little bit different from the more familiar nearest neighbor Heisenberg spin chain that I kind of assume you will have seen, of course. And I will also show that this is actually an interesting, it has various interesting applications, and it's kind of interesting from the point of view of just quantum integrability, because these long-range spin chains have a different quantum integrable structure. So for instance, if you're working on ADS-CFT integrability and you're trying to find a Hamiltonian that is really kind of relevant there at many loops, then this is a type of Hamiltonian that could appear, in fact. So it's actually rather different from some of the other Hamiltonians that you're more familiar to. And I'll also outline some of the kind of tools, algebraic tools that appear in these type of models. So they're quite different from what you see for Heisenberg. And of course, I will talk about the integrability, the deformations, and some dualities that appear there at the level of sort of algebraic level. So I think it's a nice complement to this conference. All right, so let's see. Can I actually go somewhere? It's on. It's pointing. OK, well, I'll just... It just has some lag. OK, so maybe we'll go. All right, so this is some stuff that probably everybody knows, but it's good to make sure that everybody's on the same page. So spin chains, of course, model magnetic materials originally, and it's based on quantum mechanics. Spin chains are one-dimensional models of this type. So we kind of think of a chain of spins. I will only think about spin 1/2 in this talk for simplicity, but you can go to higher rank, for instance. These models may look, not so realistic, but actually they occur in nature. So there are certain materials whose spins actually mostly feel each other in only one direction. So they're extremely well described by a one-dimensional model like a spin chain. And also they can be built in laboratory with ultra-cold atoms and optical traps and all these kind of things. Now, long-range interactions from the last point of view are actually very natural. So if you have atoms, really, they usually interact not just nearest neighbor, but they will feel each other at some slightly longer ranges as well. So they're actually important models for condensed matter physics. And these long-range models have also appeared in string theory, for instance, in condensed matter physics. And some people are very interested in them from the point of view of quantum computing, because if you build a quantum computer with qubits, then again, they will feel each other at longer ranges. So you might want to understand whether these slightly longer range interactions actually really affect what we know very well for the Heisenberg spin chain, right? We have this fantastic model in which we can compute and understand a lot, but it might be special to nearest neighbor or it might not. So it's useful to have a class of models which are longer range, and especially if they're also quantum integrable, so that we have a very nice mathematical structure to really see what the effect of these long-range interactions could be. And right, so that's the general motivation. So here's kind of the big picture which I like to advertise. So this is kind of like a landscape or a panorama of long-range spin chains. It's kind of like a parameter space. I don't claim that this contains all long-range spin chains, but it contains some very important ones. So we have 3 levels, and on the left we have just the Heisenberg XXX, XXZ, and XYZ spin chain. So we have a completely isotropic, SU2 symmetric, or partially isotropic, only SZ symmetric, and completely anisotropic versions of these models. From the point of integrability, these bottom 2 are kind of nice and easy, and the top one is rather harder. If you want to turn on kind of deform these nearest neighbor interactions into intermediate or even long-range models, then let's start at the isotropic level. So here there's on the other extreme, there's a spin chain called the Haldane Shastry spin chain, which was found by Haldane and Shastry independently at the late 80s. And it's also very beautiful. I'll tell you more about this. And in the middle, there's the Inozemtsev spin chain, which some of you might remember a bit from IPhT. Now, as you see, there are some question marks here. So this landscape is not completely understood yet. So there are some models. I mean, we're hoping that there are, in particular, some model here which kind of really, in limits, give rise to all of these spin chains here. And if this would work, and we would really understand such a model, we will really understand a lot about the integrability, even if you only care about the Heisenberg spin chain. I think we will learn a lot about what integrability really means and can look like and so on. So this is kind of the picture that I want to keep in mind. And this is kind of the outline of the talk. So I'll start with Heisenberg XXX, nice and easy. We understand it rather well. And then we'll deform via intermediate range to this long-range Haldane Shastry spin chain. And I'll show you some of its features. I will be quite qualitative. So the details you can find in our papers, or you can ask me about it later. But I would like to just give you a flavor of what's happening here. And then once we are all the way in the long-range setting on the isotropic level, then I will outline some of the algebraic tools that appear here, and they allow you to Q-deform this, so turn on some sort of partial anisotropy and break part of the isotropy, if you wish, to go to this Q-deformed Haldane Shastry spin chain. Right, so I'll start with just the isotropic level. So a typical anatomy of these isotropic spin chains are as follows. So you take, let's say, L spin 1/2 sides. We have a Hamiltonian on it, which I will take of a pairwise form. So we have pairs of spins, like here, interacting between I and J. The interactions are basically the standard spin exchange interactions, one sort of the anti-symmetrization of spins. You can write it in Pauli matrices if you want, just at longer ranges than what you're used to for Heisenberg. And then there's some pair potential here, which should be translationally invariant and symmetric. And this controls the interaction strength between sides as they go further apart. So an example of a pair potential that we know very well is the case that forces the distance between two sides to be 1, so that the sides are nearest neighbor. Another example is the Inozemtsev spin chain. It's a little bit more complicated, and it has an elliptic pair potential. So it's up to some normalization factors. It's a Weierstrass P function. If you don't know this, it's fine. It's just a doubly periodic function. So in one limit, it gives a 1/sine squared. So this is a function which, of course, has a real period. This is if you send this imaginary period to 0. To infinity, in fact, I infinity. If instead you send the real periods to infinity, you would get 1/sinh squared, which has an imaginary period, right? So you kind of think of the Weierstrass P function as a generalization that contains both of them, and it's doubly periodic. One of the periods is the length of the chain for periodic boundary conditions, and the other one is it's a parameter which controls the interaction length. So in this limit, if you normalize this correctly, you get this Kronecker delta function for nearest neighbor interactions, and in the other case, you get this 1/sine squared, which, by the way, has a rather nice geometric interpretation. If you think of the chain as sitting in the unit circle in the complex plane, then this 1/sine squared is precisely 1 over the square of the Chord distance between the two particles. So just the length, so it's 1/r squared with r the distance between these two sides. So that's rather nice. Now, the Heisenberg model, of course, comes from studying magnetic materials, as I already mentioned. The Inozemtsev model had famously a guest appearance in IPhT by Didina and Matthias, who showed that up to some loop order it appeared in IPhT, and then they went a bit further and it didn't actually really kind of hold, right? So it's but this really sparked interest in the Inozemtsev spin chain, and actually this is really the reason why Rob and I are working on it as well. So I think it has kind of rekindled the interest in these type of models. This Haldane Shastry spin chain is interesting for various reasons. One is that you can think of it as a lattice version of the fractional quantum Hall effect. So it exhibits, it's a lattice model, but it exhibits some sort of fractional exclusion statistics. So there's some sort of anyons in a certain setting, in a certain sense. And also it has an antiferromagnetic wave function, which looks a lot like a Laughlin type wave function from the fractional quantum Hall effect. So Haldane was interested in this for this reason, that it kind of has, it's a lattice version of something that he liked a lot. Another application is to conformal field theory. So it's actually realized that these models are in the same universality class as Heisenberg and actually Inozemtsev. So they're described by a SU2 level 1 Wezomina-Witten theory. But one thing that's rather interesting about the Haldane Shastry model is that in some sense it's as close as possible to being an exact truncation of the conformal field theory. So the spectrum here is extremely simple. There are no finite length corrections, if you wish. And there are certain characters that you can compute, and they really give term by term the characters of the affine Lie algebras that occur in the Wessel-Witten theory. So it's really kind of like an exact truncation. The coefficients that you compute for a certain length, they don't change if you increase the length. So it's really very nice from that point of view as well. Now, in terms of quantum integrability, of course, the Heisenberg model is a paradigm for quantum integrable models in general. The Haldane Shastry model instead is a paradigm for long-range quantum integrable models. It has a very, very special structure, as I kind of already mentioned through these properties here. And I'll show you a little bit more of this. And the integrability here looks rather different. The Inozemtsev spin chain is actually quite interesting because it really challenges our understanding of quantum integrability. So we believe that this is quantum integrable, but it's not really known whether this is the case. And in one way, this can be understood because the way that quantum integrability appears on the left is rather different from the way it appears on the right. So there should be something that really interpolates between the two. And this is a hard problem that we're working on for a long time already, and others too. And there's some progress in this direction, but it's really a long way to go before we really understand this. All right, so let me show you a little bit qualitatively what can happen. So let's take a length 6 spin chain. You just put it in Mathematica. You, let's say, diagonalize per Magnon sector, and you can compute the energies for various values of this interpolation parameter kappa, all the way from Heisenberg through Inozemtsev to Haldane Shastry. So here we see the energies, and here we see this kappa. And so at the Heisenberg limit, there is some spectrum. It looks whatever it looks like. And then there's something interesting happens. So these energy levels, as we start to increase the interaction distance, these energies, they start to move. Actually, they start to go up, and they can sometimes cross, and they really cross, which is believed to be kind of a hallmark of integrable models. So this already hints at the Inozemtsev model being integrable in a certain sense. Normally, the energy levels would repel because vectors would mix. But if there's enough symmetries, then the vectors are kind of protected and they can't really mix. So that's why these crossings are very interesting. And then as you go all the way to Haldane Shastry, you see something. Let me just finish this. Something very interesting to happen. So you see that certain levels can get close to each other and in fact merge in the Haldane Shastry limit. So there are two things that are very special in the Haldane Shastry limit. One is that these energies that occur, they're very regularly spaced. So you see that this distance here is exactly the same as the one here. It's the same as here. This is twice. This is 3 times that. This is the same. This is 4 times that, and so on. So it's extremely regular, which is related to the fact that, in fact, there are only statistical interactions, but no really bound state energies, or only real rapidity. So it's very, very special model. And then there are certain exclusion rules, like Pauli type of rules, which say which momenta you can select. And from that, you can completely write down explicitly what this energy spectrum looks like. So that, again, shows that this is a very special model. Alessandro.
Yeah. So the fact that you have energy levels merging in the Haldane Shastry limit is, I guess, you will probably explain us the result of some symmetry, I guess.
Yep, that's right.
The crossing, does it appear at random places, like just some particular level crosses some place, or
Yes.
there are like generic places where there is some enhanced symmetry that leads to this crossing of levels, which may be some other degeneracy?
We've looked a bit at this, so I'll tell more about all of this, of course, but let me outline something that's a little bit more detailed than what I will. So what we really did for the two-particle sector is that Rob and I looked at we really solved the beta equations in all the different classes of solutions, and we followed the beta roots as we varied the parameters. And something interesting happens there, but those values at which this of kappa, at which these interesting things happen, they don't seem to be related to these crossing points here. So no, this doesn't seem special in any way, except that they just have to cross somewhere, and it happens. These look like they're maybe at the same point, but this is different, and this is quite different again, and this is... So, no, it seems to, from as far as I know, that doesn't seem to really have any significance. Are there any other questions at this point? No, then I'll continue. So I already mentioned something, but let me just outline. So I would like to make a distinction between different notions that are closely related. So firstly, there's exact solvability. This means that by whatever trick, you can write down exactly the spectrum, at least in principle. So for instance, I would say that the Heisenberg spin chain was known to be exactly solvable from the work of Bethe onwards. However, Bethe's work showed that the Heisenberg spin chain is very special. You have quasi-momenta, and there seem to be quasi-excitations, and all sorts of nice things. Factorized scattering seemed to happen at the level of the coefficients. So this was not really, it's a kind of an observation, but not really understanding why it happens. So I would say that quantum integrability, for me, gives an algebraic understanding of why it was exactly solvable. So it's a deeper and more precise sense in which you're exactly solvable. And here, to be precise, I mean Young-Baxter integrability. So there should be some underlying Young-Baxter equations, kind of like a microscopic definition of integrability. And of course, this came from Fadeev and the others, and Jimbo and Miwa and so on. They did a lot of very nice work on quantum groups and related things to show that you can really understand this exact solution from an extremely nice algebraic point of view. Moreover, this also gives rise to a family of higher Hamiltonians, which is kind of, it's like a nice, if you look at the beta solution, you expect that there should be extra symmetries, and then via the connection to the 6-vertex model, Sutherland showed that indeed there's a generating function for conserved charges, so they're actually higher Hamiltonians, and so it has these higher Hamiltonians, lots of symmetries, which is good. That's kind of the quantum version from what we expect of classical integrability, and so both of these come from quantum integrability. Now, on the Haldane Shastry side, we have all of these. It's exactly solvable. It was then found to be quantum-integrable, and in particular, you can explicitly write down higher Hamiltonians. For Inozemtsev, it is known to be exactly solvable via a combination of the beta ansatz and some sort of things that happen at Haldane Shastry. And we were able to really follow, as I mentioned before, these exact solutions here, at least for the two-particle sector, all the way from Heisenberg to Haldane Shastry. At the level of the rapidities, at the level of the wave functions, we get extremely nice matches in the limits. And here there's a proposal for higher Hamiltonians, and there's a proof that the first two non-trivial of them commute, but in general it's not known that all of them commute. So at this point, this is kind of believed to be true, but it's not really settled yet. And in particular, there's no idea of what the quantum integrable structure should be at the moment. So it's kind of interesting. At the moment, I would say that this is really a model that shows that exact solvability need not be quantum integrable. Of course, we hope that, they will all come together. All right, so what I'm going to do now is I'm going to take the two-particle sector for arbitrary length, and I'm going to first start at Heisenberg, then I'm going to show you what happens at some random value of kappa for Inozemtsev, and then I'll show you a bit more about what happens for Haldane Shastry. So we start with Heisenberg. So here is a plot of the momentum, the total momentum of so this is two particles, so there's a total momentum, which is the sum of the two quasi-momenta of the separate magnons, and this is from 0 to 2 pi. And then here is the energy with some units that I've suppressed. And what you see here is that this spectrum, consists of three types of solutions, if you wish, to the beta equations. So firstly, we have this yellow one, which is just a dispersion. So if you were looked at single magnons, then you get this quadratic, the sine squared, right, as we know very well. And if you apply the lowering operator, you get solutions at m is 2. So that's what this yellow curve here means. Then there are lots of blue dots, and I've indicated kind of open blue dots and solid blue dots. The open blue dots might be slightly hard to see, but the point is that here there are solutions which have real quasi-momenta, and they're very close to their kind of bare values. So these particles interact a little bit, but very mildly. And these open circles are the energies that you would get from just looking at the, if they were free particles, just free particles, then they have their separate contributions. This is their energy. Then if you actually take into account the interactions, the energy moves up a tiny bit, but only very little. Now there's a different type of curve, which is drastically different here, and this is the bound state curve. So there are solutions which have complex quasi-momenta. For two quasi-momenta, the two are just complex conjugates, and in fact, its energy here is given, well, asymptotically, and to very good approximation for finite size, by half the dispersion. So you see that if you have momenta kind of close to pi, let's say, then there's really a gap between the bound states, at least for m is 2, and all these real quasi-momenta type of solutions. In terms of representation theory, we can also understand this picture and actually the general length picture, so it's more or less as follows. So here I draw a picture of the Hilbert space. Each dot represents a basis vector in some, a particular good basis, namely an eigenvector. And I'm ordering them per number of downspins. So this one has 0 downspins, so it's just up, 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 up everywhere. And then there's 1 downspin, these vectors, 2 downspins, and so on, all the way down to all downspins. And of course, by SL2 symmetry, we know that the big Hilbert space should decompose into SL2 irreducibles by Klabbers-Gordon. So if we have 5 sides, then if you do Klabbers-Gordon decomposition, you get 2 to the tensor power 5 is 6 plus 4 times 4, and then plus 5 times 2. So here you see the 6, 4 times 4, and then 5 times 2. Physically, we can understand this a little bit better. This is the ferromagnetic pseudo-vacuum. With all its descendants. These are the magnons, which you get from translational invariance, so they're also very simple. With its descendants, the yellow point, this here corresponds to the curve that we see here. And then there are some really m equals 2 highest weight states. And they come in 2 classes, indeed. There are the scattering states. Here, for this length that I took here, there are only 3 of them. And then there's some bound states, which would lie on this curve here. OK. So this is all standard representation theory, and it's nice. Now let's see what happens if we turn on long-range interactions. So first we go through some point of Inozemtsev, and you see things change, but mildly so. So here, the dispersion and this kind of crossing happen to go through the same point. That's no longer true here. It's not so important. You also see that the bound state curve starts moving up a bit. So it's no longer at half the bound state curve. We can, by the way, compute this exactly. It's some known elliptic function. And you see, well, if you look very carefully, you see that these 2 points are slightly closer to each other than they were on the Heisenberg side. And if you increase the interaction distance, then these points are getting closer and closer to each other. So the particles become more and more like free particles here. And indeed, this is what happens if we go all the way to Haldane Shastry. So here we are at Haldane Shastry. We no longer have open circles. They've really merged in the limit. So it really supports this claim that these particles are basically free particles that only interact through their statistics. There are certain rules that say which momenta you can pick. And besides that, they're just the literal sum of one particle energy. So for instance, if you would take, one magnon here and another magnon here, then there will be really their geometric sum will be the point exactly there, right? It's really precise additive. And the other thing that we notice is that, okay, so this dispersion became really nice. It's just a quadratic function in the momentum, so that's a very pleasant feature. And moreover, by the way, quadratic together with this exact quantization of momenta means that we get these special values that I showed in the previous plot. They're very easy to get. If you have these kind of things, they will precisely come in 2 pi squared over the length squared, and that was the units for this plot that we had before. So something else that is very interesting happened. This bound state curve in the limit really merged onto the dispersion relation. So what this indeed means, as Alessandro already anticipated, is that there's some hidden symmetry, and it turns out to be a Youngian symmetry. So you remember from the Heisenberg model, you have a Lex matrix, an L operator, and we use it for the algebraic beta ansatz. Here it's different. There's another L operator, and it acts by symmetries. There's no algebraic beta ansatz. If you act by A, B, C, or D, you all get just symmetries. So you can use the B operator to lower. And sometimes the B operator just lowers as it did, as the S minus did here. But sometimes the B operator actually can give a linear combination of what you would get from S minus and something else. And what happens precisely is that these bound states, they join with some of the higher M scattering states with real rapidities, and they become affine descendants. So here we have bigger representations because we have a bigger algebra. So here we have basically the same decomposition in terms of SU2, but as the decomposition in terms of the Youngian of SL2, some of the eigenspaces become bigger, and that's the reason for these extra degeneracies here. And if you do the counting, then actually you can see that it's true that for any M, the number of scattering states, so with real quasi-momenta very close to their bare values, is precisely the same as the number of solutions to this rule that gives the Youngian highest weight states. So what we conjecture is that this will persist to general M. At the moment, we're looking at M is 3 to see that if this persists. It becomes harder and harder, of course, but at least we'd like to support this claim with M is 3. That would be rather non-trivial, but I'm quite convinced that it will work. So the lesson is that here, so it seems to be the case that Heisenberg bound states, at some point for Inozemtsev, they basically unbound and they become descendants instead. They get just real quasi-momenta in the limits of Haldane Shastry, and they really sit together with some lower M scattering state. So
can I think of this saying that the binding energy is 0?
That's right. That's right. So what happens is the following. So exactly. So this is really interpreted by Haldane as a free gas of anyons, of specific anyons. And actually, if you do higher rank here, then the rank determines the kind of statistics that you have. So there's a simple exclusion rule. Namely, if you have your momenta equally spaced, you can, for SL2, you cannot pick 2 neighboring momenta. So, if you have bosons, then you would be able to pick the same momenta many times. If you have fermions, you can just not pick the same momenta. In some sense, these are like fat fermions. They also take up the neighboring spaces. So that's the only rule in which they interact. So this is called exclusion statistics. So they have some sort of statistical interactions only, but there's no binding energy. That's exactly right. All right, so we are seeing that this Haldane Shastry model is really rather special and quite different from the Heisenberg spin chain. And here is a short kind of cartoon of how it really works. So here at the bottom, we have the Haldane Shastry spin chain. And the algebraic setup is that there is some algebraic structure called the degenerate affine Hecke algebra, which in some, its center in some representation gives rise to the Hamiltonians of the trigonometric spin Calogero-Sutherland Hamiltonian. Before we get there, let's actually do something simpler. This thing has a representation just on polynomials, and this is an old and well-known story. It corresponds physically to the trigonometric quantum Calogero-Sutherland model, and it's known to have lots of commuting Hamiltonians and exact closed-form eigenfunctions that are extremely nice. They're called Jack polynomials. So there's some sort of symmetric polynomials that are very, very well understood from a mathematical point of view. So if we take this simple representation, we get this quite simple model of particles, scalar particles moving around. Now, what we can do is we can give these particles spin, and it turns out that this also has a representation of the same algebra with the family of commuting Hamiltonians and some exact eigenvectors. But moreover, by something called affine Schur-Weil duality. This is due to Drinfeld in the 80s. Representations of this degenerate affine Hecke algebra also give rise to a representation of the Yangian. So in fact, this trigonometric spin Calogero-Sutherland model also comes with an action of the Yangian. And it turns out, and this is not so hard to see algebraically, that this really commutes with this here. Moreover, the Hamiltonians, they come from the centers of the two, which essentially coincide. So the center of the degenerate affine Hecke algebra and the center of the Yangian both give rise to the commuting Hamiltonians here. And since it's the center of the Yangian, all of the Yangian commutes with it. So A, B, C, D are all symmetries. Center, by the way, is generated by the quantum determinant. So it's a bit different from the usual trace that we take for the XXZ spin chain. Now, this trigonometric spin Calogero-Sutherland model, it has particles moving around with spins, and they interact in pairs, quite like actually what happened for the Haldane Shastry spin chain, and this, again, is no coincidence. There's a special limit in which is called freezing, in which, well, physically what you do is you send the coupling constant to infinity, or equivalently, you send h bar to 0. So it's some sort of semi-classical limit. The spins stay fully quantum, but what happens is that the potential energy starts to dominate the kinetic energy. So the particles, in a way, start to move slower and slower and slower, and they want to sit at their equilibrium positions. And if you do it carefully, then you should see that they want to sit at their classical equilibrium positions, which are precisely equally spaced. They're no longer moving, but they still have spins that interact with each other long range in pairs. And that's how you get from these Hamiltonians here, the commuting Hamiltonians of the Haldane Shastry model. Moreover, since I said that the Yangian acts by symmetries, there's no algebraic beta ansatz that we can do. But what you can do instead is, with some work, you can show that the number of the downspins here, so the magnons, are actually governed by a very special version of this scalar Calogero-Sutherland model, which is extremely nice because we know its exact eigenfunctions. They're these Jack polynomials. So Jack polynomials in just the number of downspin many variables with a very special value of the coupling constant precisely give the eigenfunctions of the Haldane Shastry spin chain. So this is very special. This is a closed form solution. So there are no beta equations to be solved. This is really completely exact and explicit. All right. Well, this was just a cartoon. Of course, there are details. Let me mention again. So there is actually a duality playing here. So you know from representation theory, maybe Schur-Weil duality, you have the symmetric group acting, and it commutes with GLN or Lie algebra GLN acting. And there's an affine version of this, which relates representations of the degenerate affine Hecke algebra with relations of representations of the Yangian. So that's one example of a duality that shows up in these long-range spin chains. Are there any questions at this point? So this was what I wanted to say about the isotropic models, and now I'm going to kind of take off and go into the Q world, so start to really deform in another way. But I think it's a good moment to see if there are questions.
Maybe seeing as we're at this point now, you said there's you have this algebraic description of the Haldane Shastry, but there is no known algebraic description of the Inozemtsev.
Yeah, that's right.
Are there ideas for whether there would be new mathematical structures that need to be introduced, or?
So it's a work in progress. I cannot say too much about it. There are some ideas for sort of this side of the story. This side of the story, it does not work there. So really, this sort of quantum group kind of action or anything towards an algebraic beta ansatz.
When you say does not work, you can prove that
if I do the same that I know how to do for Haldane Shastry, it does not work for Inozemtsev. Okay. So really something completely new will be needed if we want to understand a similar picture for the Inozemtsev spin chain. So that's what I mean by kind of quite interesting. If we would manage to do this, it would really completely change, I think, well, both mathematically in terms of representation theory, but also physically in terms of integrability, what it means, what it can look like to be integrable. So it's a very hard problem, of course. Any other questions? Okay, then I'm going to continue. Right, so I think we're halfway the talk more or less, and that makes sense because we're now going up to the second level. I'm not going to talk about the third, so we're halfway. And in fact, a little bit over. So, okay, so this is the same picture as I had before, and the representation theory is very nice. Everything is understood how to Q-deform the previous setting that I showed you. So rather than the degenerate affine Hecke algebra, here we have something called the affine Hecke algebra. It is quantum affine Schur-Weil dual to quantum affine algebras or quantum loop algebras. It's only level 0 representations, so they're just quantum loop algebras. And if we start again with the affine Hecke algebra, then just like the degenerate affine Hecke algebra gave rise to commuting Hamiltonians and eigenfunctions, joint eigenfunctions of the trigonometric Calogero-Sutherland model with Jack polynomials as wave functions. This affine Hecke algebra, by work of Cherednik, gives rise to the trigonometric McDonald-Ruijsenaars model. So it's kind of interpreted as some sort of relativistic or difference version of the Calogero model. And it, again, has extremely nice eigenfunctions that are called Macdonald's polynomials. They're a very nice family of symmetric polynomials that are very well understood mathematically. And this, again, comes from the center. Now, you can, once again, introduce spins, and you get a spin version of this trigonometric Macdonald-Ruijsenaars model. And then you can repeat the same. Well, this model is special in that we have both commuting Hamiltonians coming from the center here. We have exact eigenvectors sort of coming from the center here, and moreover, we have an action by symmetries of the quantum affine algebra. And it's still true that the Hamiltonians are also generated by the quantum determinant on this side. So the picture is really the Q deformation of the previous picture. And then by freezing, so taking the same limit, this time you get, well, again, a spin chain of equally spaced particles, which now interact in a much more complicated way that I will show in a moment. And this is a Q-deformed or partially isotropic or XXZ-like version of the Haldane Shastry model. Again, its wave functions for M down spins are governed by an M particle version at a very special value of the coupling of this trigonometric scalar Macdonald model. So we have very nice eigenfunctions explicitly in terms of Macdonald's polynomials. Moreover, I mentioned that here for Haldane Shastry, the only interactions were through the statistics, and there was a very simple rule. You could not pick two neighboring quasi-momenta. This rule does not change. So this is still completely statistically interacting otherwise free particles. So it's very, very simple. It still has fractional statistics in the exclusion sense, and so on. Right, so now, before we go here, I want to use another duality and go to a sense. So this affine Hecke algebra that I have here, it has a duality. This was found by, well, really it's a double affine Hecke algebra that has a duality by Cherednik. And so rather than picking the representation that is relevant here or really here, you can take some sort of dual representation in a precise sense. And this gives rise to, so we have again the affine Hecke algebra, and it gives rise to the inhomogeneous six-vertex model. So what I mean is that the representation that you get here can be understood as being related to the inhomogeneous six-vertex model. By quantum affine Schur-Weyl duality, it comes again with the action of the quantum loop algebra with an L operator that is dual in the sense of Cherednik to the L operator that we had for the spin Macdonald-Ruijsenaars model. And here, there's something that's a little bit similar to what happened for Haldane Shastry. So we can take some logarithmic derivative, as we know very well, to get something that I would want to call the inhomogeneous Heisenberg spin chain. You might not have really thought about this, but I'll show you more about this in the next slide. And then we can take a special limit, the homogeneous limit, in which all these inhomogeneities become the same. And then we get our good old Heisenberg XXZ spin chain. So the picture here is a little bit similar. An important difference is that here, rather than taking the center of the quantum affine algebra, as you know very well, we use, to get the Hamiltonians here, what we get here is the transfer matrix, which corresponds to an abelian subalgebra called the beta algebra. So it's something else than the center. It's larger, so it commutes with less. And here we can take logarithmic derivatives, and then we get all these commuting Hamiltonians of the inhomogeneous and in the limit homogeneous Heisenberg XXZ spin chain. So the picture is somehow, in a precise sense, at least at the top, is dual to the picture that we had for Haldane Shastry. So I think this is rather interesting, and more there is to be understood. In particular, coming back to Inozemtsev, it would be really kind of wild to have some sort of something that interpolates between these two dual sides. It sounds like it might be rather difficult, but it would be really cool if it works. All right, so I showed this, what I call the inhomogeneous Heisenberg spin chain. We think of it as a Heisenberg spin chain where the particles are not equally spaced. So let me show you more about this. You kind of, in a way, you already know it, but you might never have really thought about it. So let me first motivate this. So normally we think of inhomogeneities as a computational tool. For instance, if you want to prove the completeness of the solutions to the Bethe equations, then it's much easier if you introduce small inhomogeneities. You kind of break most of the symmetry, so you can easily count solutions. And so you can show that the Bethe ansatz is complete by introducing small but finite inhomogeneities. Also, the proof of the Razumov-Stroganov conjecture used inhomogeneous six-vertex model and inhomogeneous XXZ spin chain to really show this. So this was a very nice observation first for a relation between spin chains and some loop model eigenvectors. These inhomogeneous spin chains also occur quite naturally. For instance, in n equals 2 supersymmetric gauge theory, you have this Bethe gauge correspondence by Nekrasov and Shatashvili. So there, you naturally get Bethe equations which have inhomogeneities. And the reason for this is that in terms of geometric representation theory, which is the mathematical version of the Bethe gauge correspondence, if you wish, these inhomogeneities are interpreted as equivariance parameters in equivariant K theory. So mathematically, they're extremely nice as well. Now, more physically, inhomogeneous spin chains are interesting for CFT. So if you take unimodular Q and the scaling limit, where Gleb Kotousov can tell you much more about this, then you get interesting, by introducing inhomogeneities, you get a more rich landscape of CFTs there. And moreover, of course, these inhomogeneous XXZ spin chains are interesting for other limits. For instance, quantum but non-affine Godin models occur as a special limit of these inhomogeneous XXZ spin chains, and various other things also occur as special limits. For instance, you can take the staggered 6-vertex model and the staggered XXZ spin chain, where you take two different, like periodically two different inhomogeneities, and then you get slightly longer range interactions. Okay, so this is a motivation for this inhomogeneous Heisenberg spin chain. By the way, remember that I'm really talking only about finite length here. So what we do is the usual thing. So we take an R matrix, the 6-vertex or XXZ R matrix, which obeys all our favorite identities, the Young-Baxter, unitarity, and initial conditions. And then we make the transfer matrix, which is graphically, so here I have a product of R matrices, and then I take the trace over it, which I indicate by these little arcs. So graphically, this is the transfer matrix, and here you see it in terms of a trace over the auxiliary space of R matrices. Now, of course, we know that because of the Young-Baxter equation and generic invertibility, this thing here of the R matrix, this thing here forms a commutative family of operators, so it's a good generating function for Hamiltonians, and that's what we do to get the inhomogeneous Heisenberg spin chain. So in analogy with the homogeneous case, I define the inhomogeneous Heisenberg spin chain Hamiltonian as the logarithmic derivative of the transfer matrix, but we have to do it at a particular point. And in this case, the good points are precisely the inhomogeneities, because that's where some of these things simplify. If I pick any one of these, if I pick this U to be any one of these inhomogeneities, then we can use this relation here that says that if two lines meet with the same spectral parameter, then you just get the permutation. So the thing kind of breaks open. So these are the good points to do it. So we get L different Hamiltonians, Hj. So let me kind of talk you briefly through the graphical computation of this. I think it's rather nice. Of course, it also works in a homogeneous spin chain, so you can nicely compute it graphically. So first, let's think about this derivative. So this transfer matrix is a product of stuff. So its derivative is a sum of things where we take the derivative of any single of the factors. So that's what I do here. So I indicate this derivative by a big dot on the R matrix. And then this derivative can either be to the left of the point where we which of the inhomogeneity that we took. It can occur at the same point, or it can occur to the right of the point where we broke it open. So of course we set this U to be Zj. So indeed these R matrices here, they open up just as governed by this rule, by the initial condition for the R matrix. Now there's a little bit of trickery. Of course, here we can see some simplification. So this here is precisely a copy of this unitarity picture. So we can pull this line all the way to just to the right of the Zi, and the same here. So we can pull it all the way to just to the right of the Zi. Here we cannot really simplify it so much. Now in the computation, the next step, which is a little bit non-trivial, is to notice that basically, well, I guess I should really draw this. So we have now reduced our computation to mostly these type of pictures. We have an R matrix here, and then the derivative of the R matrix here. And what you can show is that this picture here simplifies to something nice. Namely, it basically becomes what I here denote by this wiggly line. So if you take the up to a factor, the derivative of the R check matrix, which we know is the local Hamiltonian in the homogeneous case, then I'll indicate it like this, and this picture that I showed on the blackboard there becomes some function, which I denote by this potential. It's quite simple. I'll get back to it in a moment, times this usual derivative, this usual local interaction. So graphically what happens is that now, up to some factor, we have this zigzaggy line. So what happens is that this particle at site j always goes to any point to the left of it and then interacts via the usual nearest neighbor interaction. And this transport happens via R matrices, because all these crossings here are R matrices. Then if we have this, basically the same happens. The particle at site j always wants to go to the left, and if necessarily, periodically to interact with the particle that we took the derivative at. And then there's something kind of funky. What happens here is that the particle at side J goes to the left. Then it comes back to its own side. It kind of interacts with itself in the future. It goes back to the right to interact with itself from the past, and then it continues. So you can make a sense of this algebraically. It's kind of simple. What you do is just you write the R matrix of a product with some coefficients of a unit, like any one of the basis matrix in the left tensor factor and then any one of the basis matrix in the right tensor factors. And then you just have lots of R matrices in between. So you can really write down formulas. I can put this in Mathematica, and it's completely happy to check that these things commute for different J, for instance. So these interactions are rather non-trivial. Let's just understand them a little bit better. Let's send all these inhomogeneities to 1. Then what happens is that I can basically use this picture everywhere where I don't have, well, this picture from the derivative. So all these things open up, and what happens is that you just get nearest neighbor interactions always. And that gives back the usual nearest neighbor Heisenberg spin chain. All right? So if you don't like the inhomogeneities, you can do the same graphical computation to get the usual Heisenberg Hamiltonian, but it's actually not too much harder to do the inhomogeneous case. Now this function here, if you would write this in additive notation rather than multiplicative, it looks just like a Q deformation of the 1 over sine squared that we had before. This is quite easy to see. So it's kind of like a point splitting of the 1 over sine squared. So it's actually not a kind of a very strange function to appear. And I've just normalized this here by something so that I can take both the homogeneous limit and I can send Q to 1 and there are no singularities. So this here is the inhomogeneous XXZ spin chain. Of course, we kind of secretly all know this because let me just repeat it. So this is the same Hamiltonian that I just computed for you. Of course, we know that its exact spectrum just comes from the algebraic beta ansatz with inhomogeneities up to solving beta ansatz equations with inhomogeneities. But this is a standard computation that we've all done. So here I show you the Hamiltonian of the thing that we've been diagonalizing in those exercises where we included inhomogeneities. Now, we get back to the Q-deformed Haldane Shastry, which is related to this Daha duality of Cherednik. And I'm just giving you what the result looks like. So it looks a little bit complicated, but actually it's simpler than this inhomogeneous Heisenberg spin chain. So the Q Haldane Shastry Hamiltonian is the sum over pairs of sides. And this, we only have this interaction where the spin goes from the right to the left, just like it did in the first part of the sum here. To interact with Zj here, and then it moves back. And here, all the transport is by R matrices, and this local interaction is just the usual exchange interaction. So here we only have the simple part, really, of this thing here. There's no of this periodicity happening and none of this weird stuff happening. And then there is, again, this potential, which here, actually, I don't need to normalize because by freezing, which I mentioned, these values of z, the coordinates of the particles or the inhomogeneities, they have to be fixed to the jth power of the primitive lth root of unity. So again, these are the positions of the particles sitting on the unit circle in the complex plane. Then the jth particle is just the jth root of unity, so equally spaced and nicely. So you take this somewhat involved expression and you evaluate it, that's how we call this, the inhomogeneities to these specific roots of unity, and that is the Hamiltonian of the Q-deformed Haldane Shastry model. So it looks complicated, but it's less complicated than the one that you've secretly already known all your life. And moreover, if you take Q to 1, then this function here just becomes the 1 over sine squared. And this thing here just becomes the anti-symmetrization. So this is just a Q deformation of the Haldane Shastry model. Moreover, this deformation here is precisely so that all the nice properties generalize, as I outlined. So in particular, it has quantum loop symmetries, so lots and lots of symmetries, big eigenspaces. And we can understand its exact spectrum via some connection, as I already outlined, to the Ruijsenaars-McDonald model. And we have exact wave functions, which are, in terms of these McDonald's polynomials, in closed form, no beta equations to solve. So in some sense, the spectrum, the models may be more complicated than normal XXZ, but the solution is much easier. So it's very delicate so that everything works extremely nicely. And of course, it's a long-range model. And moreover, it's actually a multi-spin model. So if you think of this as the R matrix, then what can happen is that if you have a downspin here, the downspin can either go to the left or it can kind of drop off this line. So really, multiple spins can interact at the same time. So the interactions are rather complicated. And I understand from Didina that she thinks that the ADS-CFT Hamiltonian might well be long-range and multi-spin interaction. So when she saw this formula the first time, she was very enthusiastic because it was getting towards what she was hoping would be relevant for ADS-CFT integrability. Now let me just advertise something that we've been doing recently with our master student, Ayman Tufik. So of course here, compared to normal Haldane Shastry, we have this parameter Q, the deformation, and you can play with this, and in particular, you can take some nice special points. So one thing that you can do is you can set Q equal to I. the simplest root of unity, non-trivial root of unity. And for Heisenberg, it's well known that this is related to free fermions. You can do a Jordan-Wigner transformation, very simple. In momentum space, the Hamiltonian becomes diagonal, and you can just read off the spectrum. So here, everything is much more complicated because these interactions are more complicated. But we can prove that, in fact, it is a free fermion model in the sense that there are fermionic operators, F and F dagger, so that this thing is really, in the end, quadratic in F and F dagger. So it's just a model of hopping, long-range, complicated way hopping, free fermions at Q is I. Moreover, if we take odd length and we make sure that the Hamiltonian is kind of regularized in this limit Q going to I, then we have, it's quite interesting, a massless relativistic dispersion relation. So it's really just has two branches away from the origin, just like a standard relativistic dispersion for a massless particle. And for even length instead, all the eigenvalues become 0, but we get Jordan blocks, and we get rather big Jordan blocks. So this is quite interesting. This is, for the Heisenberg spin chain, there's a special version which is UQ SL2 invariant, and that 2 is known, if you take Q to I, to have Jordan block structures, but in that case, the biggest Jordan blocks are always just 2 by 2. We get arbitrarily large Jordan blocks, and I think it has to do with the fact that we have much more symmetries, and these Jordan blocks are somehow related to the affine descendant structure. But this is something we don't really understand yet, and we're working on. Moreover, we're trying to get an...
In this given L, you're recovering this Q-deform structure at roots of unity?
I mean...
Q-deform takes example is work by deformation of the Grenadina who started exactly...
No, so it's different, as I mentioned. So what they often... No, right. So if you do normal Heisenberg xxz at Q is I, you can either do the periodic one, which is you do Jordan-Wigner, or you can take one of these UQ SL2 invariants, for instance, the open one, or this sort of braid translate quasi-periodic one, which they like a lot because it's related to temporally Lieb and quantum SL2 and all these kind of things. Now, if for the latter you specialize, then, as I mentioned, you get Jordan blocks, but it's much smaller. So in terms of representation theory, here we seem to have a different type of free fermion model, which has kind of a richer representation theory, which maybe is not so strange because we started with a model with richer representation theory. So, but it's very nice to see it actually work in practice at this special point. Of course, this model, so we're hoping to find an explicit expression just in terms of the fermionic operators of this Hamiltonian. For even length, it's not too hard probably, and I'm sure that we will be able to get such a formula. For odd length, more terms survive the limit and it's harder, but maybe we would be able to get it. And I think this would be rather nice because this could be an interesting model for condensed matter physics. Okay, so this is really already the outlook of my talk, so I guess I'm a bit ahead of time. But so let me just get back to this landscape. I've shown you from the Heisenberg xxx, which we know very well, how to go by turning on intermediate range interactions and then long range interactions, what happens to the spectrum via this beta ansatz exact solution through Inozemtsev all the way to Haldane Shastry. In terms of representation theory, we understand Heisenberg very well, and we understand Haldane Shastry in some sense even better. It's even nicer. There are no beta equations and so on. Inozemtsev, we don't know the algebraic structure, but it is exactly solvable, and by looking at the spectrum, we expect it to be integrable. And then once we understand the algebraic structure of Haldane Shastry, we are able to Q-deform it to get a partially isotropic version of it. And I showed you that actually, even though the Hamiltonian looks a bit complicated, it's very closely related to something which is not quite the Heisenberg xxz, but the inhomogeneous version thereof. And in some sense, those two models, or really their kind of parent models, the spin Ruijsenaar-McDonald here and the inhomogeneous six-vertex model here, are dual in the precise sense of representation theory. So I think this is a very appealing picture. And of course, it would be fantastic to try to fill in some of the blanks in this landscape. This one here is the first one to be filled in. There's some related work which gives a spin chain which is an elliptic spin chain. So it looks like it deforms Haldane Shastry, but it does not deform Inozemtsev, and so it doesn't really fit in this landscape here. And then, of course, if we go to the fully elliptic in terms of quantum groups level, this is going to be a very tough problem. But if we can understand something there, it would be amazing. And I think we will learn a lot about integrability in general. And just, so what I really advertise is this underlying picture of, well, so first I should say, of course, what we want to do is, now that we're kind of here, we want to conquer the rest of the world and understand everything, including all the Heisenberg limits. And I think we will learn new things about Heisenberg in this way. And the underlying picture that we always have in mind is this picture of quantum many-body systems without or with spins. And this is precisely what happens for Haldane Shastry, which is related to trigonometric Calogero-Sutherland. It's Q-deformation, which is related to this Ruijsenaars-McDonald. And then, hopefully, Inozemtsev is somehow related to an elliptic version of Calogero and Ruijsenaars. And this limit is extremely hard to take from the elliptic model, but it should be something like a Lieb-Lininger model, which has some sort of contact interactions as well, but in a continuous sense, so it's much less regular, and we can't really take this limit. But I hope that we can actually understand the Heisenberg spin chain in some sense by freezing these type of models really understood as properly as the limits from these elliptic models. So I think this would be a really new and nice point of view, even for the integrability of the good old Heisenberg spin chains. So yeah, that's all I wanted to say.
Thank you very much for a nice talk. Questions? So maybe I can start. I have a couple of questions. First, can you just go back one slide? Do you have reason? Are there sort of concrete reasons to believe that this world that you want to conquer exists?
Optimism, for sure. I think. So I think that the fact that, so nowadays, I didn't really mention this, but nowadays people in quantum many-body systems are working on this thing which is called the double elliptic system, which is kind of elliptic both in the coordinates, like all of these, and in the momenta. And this is very hard, but people are currently working on it. And so I'm sort of hopeful that one could freeze this in some sense, and if one can, then it should correspond to this model at the top. So various bits and pieces are already in place.
So there are kind of, the other question I had was, you had this, let's see if I can remember. So you had this relationship between Heisenberg XXZ and Q-deformed Haldane Shastry.
In terms of the Hamiltonians or this previous?
This story. So you first did this duality and then...
Right.
How does this sit inside your picture of 9 models and...
yeah, that's a good question that I don't really know the answer to. So this Cheretnik duality seems to, in a slightly suitably modified sense, kind of in some sense reflect the picture through its middle, but I don't know what it does except at the straight boundaries.
Does it work in the at the bottom at the rational level?
Yes, it does, but the rational level in terms of the affine Hecke algebra is much nicer than this degenerate affine Hecke algebra. So here you take some sort of limit which breaks a little bit the symmetry of the Cheretnik duality. But in principle, it should also work here. Yes, but it's actually mathematically the Q deformed level is actually nicer than the isotropic level. But yes, it should work. I kind of have to work out the details, but I'm convinced that it will work.
Maybe can you just...
do you think there exists this affine duality for elliptic Daha or not?
Well, do you think elliptic Daha exists in the appropriate sense?
There are a few people that are proposing it.
Right, so there is Eric Rains and company. So they have a construction of what they think of as an elliptic Daha, but it's some sort of construction in terms of sheaves and blah, which I don't really understand. In particular, there does not seem to be a presentation in terms of generators and relations. And I only understand this duality at the level of certain, an explicit map on the generators. So, yeah, no, I've asked Rains, and he's not able at the elliptic level to give such a presentation, which would be the concrete tools that we need to really do any computations. So unless I would learn a lot of geometry, I'm certainly not able to do this.
Because there is also this, Bernstein-Plücker formulation, which also allows, but there is no algebraic formalism for it.
Right. That's true.
So, is there any example of a long range or intermediate range for other algebras? Like if you would include not only identity and permutation, but decay as well, like the trace operator, or?
Right. So.
Is there
Indeed. So let me go back to my favorite picture. Here it is. Yeah. So on this side, we have lots of things that we can do to these spin chains, right? We can go higher spin, we can go higher rank, we can make open boundaries, we can do a twist. There are lots of things that we can do. So here, so let me talk about this limit, because if I don't understand this limit, then I'm never going to understand the middle. So at this level, the mathematics was really kind of rigid and very powerful, but so it doesn't allow everything that we were able to do here. So what you can do for Haldane Shastry is you can't go higher spin. What you can instead do is higher rank. This connection with the affine Hecke algebra seems to need kind of always, if you have a k-dimensional space for your spins, then you have to have an action of GLK to make this connection via Schur-Weyl duality. And so that's one restriction, but you can do arbitrary SLK. So that's already kind of good. So in some sense, higher rank models exist. And as I mentioned, this is related to different types of exclusion statistics. So you kind of, this K in some sense is a parameter that scrolls through different types of anyons, if you wish. Now, twists do not seem to be possible in this world. But open boundaries are possible. So for Haldane Shastry, this is known. For Q Haldane Shastry, I'm planning to work on it, and I have a student, a PhD student who will start next year, and we'll look at this. So I think that absolutely it should work, and it should relate to Kornwinner theory. So there are McDonald polynomials have some sort of type BC analog, which are known as Kornwinner polynomials. And again, I'm quite confident all the structure exists, all the algebraic machinery is present. So it's just a matter of working out the details, and I'm quite convinced that we can do arbitrary 4-parameter K matrix type of things there.
Sorry, just another precision. I'm wondering, when you mentioned this double elliptic
Right, so let me go
structures,
there.
yeah. I don't know. Do you know if there is because people like have this double elliptic Mann triples, and they can show that there is this correspondence to the spin arrest models. Do you know any relations to your framework? If I'm not asking about probably spin elliptic arrest, but at least trigonometric, which would be probably more relevant.
Right. So no, I do not know about this. Do you know, are they quantum or classical spin Reisners?
I think they also have quantized.
Okay, so I'm not aware of this work. I don't know about this work, and I cannot comment on this, unfortunately. It sounds
because
interesting.
I think that if somebody understands this double elliptic reduced to the at least trigonometric spin rest, then there would be many answers to the uplift.
Yeah, absolutely. This sounds like a very fruitful direction. Thank you.
So are there any further questions? If not, let's thank Jules again for a very nice talk.